Let's play a game. I have a deck of 7 red cards and 5 blue cards, and you are going to draw cards until you draw a blue card. I'm going to give you a different amount of money depending on how long it takes you to draw the blue card. So if you draw on the first card, I'll give you $2, on the second card $1, on the third card nothing, and on the fourth card, or more, you'll lose $1. You'll give me $1. The expected value will let us determine whether or not we should play games like these. Given a probability distribution, the expected value of the experiment is just the outcomes multiplied by the probabilities, all added together. It tells you what to expect on average from the experiment. So let's look at an example. This will be abstract. We have this probability distribution here where we have 4 outcomes, 1, 2, 3, and 4, each with a given probability. The expected value is just going to be 1 times 0.2 plus 2 times 0.4 plus 3 times 0.35 plus 4 times 0.05. In other words, we take each outcome and multiply by its probability. So 1 times 0.2 is the first one, 2 times 0.4 is the second one, and so on from there. When we multiply these across and then add them all together, we end up with what's called the expected value, which is 2.25. This number means that if we perform this experiment many times, on average we would expect the outcome of 2.25. Going back to the card example, we had 12 cards, 7 red and 5 blue, and the results are given in this table here. Should we play? What would the expected value of this experiment be? So we draw this in a table, and the best way to figure out the probabilities of each of the payouts, which are the outcomes that we're interested in, is to draw a tree. On the first draw, you can either draw a blue card, in which case you're done, or you could draw a red card, in which case you would have to draw some more. So the blue branch ends. From the red branch, we can either draw a blue card when we're done, or another red card. After 3 draws, the tree will look like this. Notice we don't have to keep on going from that red draw. If we draw another card after that particular red card, we're done because we'll have 4 plus draws. Now the probabilities are just based on the cards that we have. There are 12 cards total, 5 of them are blue, 7 are red, so our first branch of probabilities is this. Then 11 cards left, so 5 and 6, and then 10 cards left, so 5 and 5, and we get our probabilities. Each of these branches leads to a particular outcome. Win $2, win $1, win $0, or lose $1. And so we can write these outcomes down in our table. And each of their probabilities are going to be given by those particular branches in the tree. So $2 is the first branch, which is 5 out of 12. Winning $1 is only arrived at that branch, so 7/12 times 5/11. Winning nothing, or breaking even, is only arrived at that branch there. So we multiply those 3 numbers together. And then losing $1, you get if you ever draw your third red. So we multiply those 3 numbers together. If we put down their decimal approximations, they're these numbers here. So to find the expected value, we just multiply each of the outcomes by each of their probabilities. The expected value of this particular experiment will be $2 times the 0.417 plus $1 times the 0.265 plus $0 times the 0.159, and 0 times anything is 0, so that term's going to disappear, and then plus negative $1, so we're going to subtract this part, times the 0.159. When we multiply these out and add them together, or subtract in the last case, we get 0.94. This is a positive number. So what we'd expect is that on average, we'll win 94 cents. This doesn't mean that you'll ever actually win 94 cents. You can only win things in increments of dollars. But if you play often enough, you will average out to winning 94 cents per play.